the fandom and the actors. It's different than Spaceballs, because Spaceballs is like.
Good morning, everybody. Apparently, I didn't realize I was going to touch so many nerves with my my silliness on the slide. But yeah, right? Star Trek is amazing. Make sure that you don't do section 5 of this chapter. Okay, just ignore it. It doesn't exist because they're talking about semiconductors way too early. Okay, and then you're gonna run into in our book. You're gonna see it on the interwebs, videos, YouTube's. Phasers always get brought up in the context of AC circuits for a good reason, but we're not gonna worry about it. Short version is a phasor is a rotating vector. And it sounds as bad, and it's as bad as it sounds. Okay. So it's just, I will maybe, if you're nice to me, show you a little phasor here at the very beginning, and then we'll ignore it after that. Okay, right? But yeah. So what the heck is going on here? We left off last time with this idea, right, that the entirety of the power grid, all electrical production, causes current to alternate, to flip direction back and forth. And in the United States, it flips back and forth 60 times per second. So what we're going to do now is we're going to try to take everything we maybe learned about DC circuits in the last unit and try to bring it forward to talk about, well, how do we deal with, right, a circuit where instead of the charges being like pushed by the battery through the circuit in a single direction, right, which is what all the circuits we did last time, how do we handle the fact that a charge in an alternating current circuit, the current's going this way, and then it turns around and goes back the other way, and then it turns around, and back and forth, back and forth, back and forth. What is a charge in a wire doing in an AC circuit? It just wiggles back and forth. So when you plug something into the power, right, it's not like charges are moving to your device. They're just wiggling back and forth. The charges actually don't ever go anywhere. Their average displacement is 0. So how does power, how does energy, how does anything happen, right, in this wiggle back and forth? Well, the answer is we pretend like it doesn't. So we can deal with wiggles. We can go back to all the wavy blah 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 stuff that we did from physics 2a, right? And then start applying that to all of our electric fields, and then have to go learn differential equations, be able to understand that, and bring some phasors, which are rotating vectors. It just goes back really fast. And so what everybody does, not just us, but electricians that work for PG&E, or the electrician that comes and works at your house, everybody, what everybody does is we cheat. We cheat and say all of that's too hard, except for the very, doctorates in electrical engineering that want to deal with it. And everybody else treats an AC circuit as if it were a DC circuit. So how do you do that? Right? So what's going on here is we are sweeping under the rug quite a bit of stuff that's actually going on. And so for this first part, my intention is to totally blow your minds in the sense of, oh, that's not in the sense of it's cool, but like, oh my gosh, that's hard, and then show you what we're going to do instead. I just want you to kind of have a little bit of appreciation for how bad this can get, okay? So, yeah, all right. This is a simulation, okay? It's easier to run simulations in class because they don't break. Actual equipment does break. So, what have I got here? This is a chart, okay, of the voltage through a resistor when it's connected to an AC power source. So like a generator, right? And in time, what we're seeing here is that this voltage right, across the resistor, the voltage through the resistor, oscillates, which as we expect, right? As that generator turns, it should do this thing, right? Okay, all right. So that's all fine and good if that's just a resistor. But we know about other circuit elements. We have capacitors that we can put into our circuit, like what happens with them. And then if we stick a solenoid in the circuit, a solenoid in a circuit is called an inductor, then that's going to do something as well. So when we go in and we say, okay, well, what does the voltage across the capacitor look like? What does the voltage across the inductor look like? What the heck is going on? Play it again. Do you see all the little diamonds following their curves? Are they doing stuff at the same time? Like, are they all equal at the same time? No, right? They're all doing something kind of, I mean, look at that. The voltages across the capacitor are not hitting their peak values at the same time as the voltage across the resistor. And the inductor's like behind everything. It's like, ah! And because you guys are smart, there's the phasors. Right? This can get bad pretty fast. And just so that you guys can really appreciate what's going on here, okay? The rotating phasors map onto the waveforms, right, for these things. So it does require quite a bit of time and math and all kinds of stuff to work through what's going on here. What I'm going to do is I'm going to summarize, right, the cheat. The thing that lets us ignore everything that we just saw. Because there's time dependence in here. Like, from the time you turn something on, there can be lots of stuff going on. So we're going to try and get rid of that time dependence, take a step back and say, okay, we know we're lying, but it's a good lie because we can do useful things. We can make the circuit, we can design the transformers, we can do all these kinds of things, and it just works. So, what have I got on the screen here? One of the things we've got to do is, so one of the prices we're going to pay for this cheat is the fact that we're going to have to do a little bit of statistics, in quotes here. We want to get rid of wavy things, okay? You can take an average, right? For things that are kind of varying in time, you can take averages. The problem is, look at the blue curve, where the blue line here is a sine function, okay? What's the average of a sine function? It's 0, right? It spends just as much time above the x-axis as it does below. And so when you average that out over time, you get 0. And 0 is a nice number. I mean, I can integrate 0 all day long, but like, it's not useful. And so we're going to borrow an idea from statistics. And it's called the root mean square. So what statisticians do this. This is how you get an average of something whose regular average is 0. So let's say you've got like a whole series, the thing that you want to find the average of that's usually 0, right? Okay. If you square the thing, and that's what I've done. I've taken a sine function and I've squared it, and it's that orangish, yellowish, baby poop brown color, whatever the color is, right? Okay. Do you see how the square of the sine always remains positive? Okay, so we square it first. So we know we like have this problem where all of our values are kind of too high, right? Then we take the average, right? You square it, you take the average. So in doing that, when you take the average of the square of the sine, you get a number that's above 0, whatever it is, okay? And then to fix the fact that you've squared everything originally, what do? Take the square root, right? So square it, then average it, then take the square root. This is the definition of something called the root mean square. You can apply it to individual populations, you can apply it to functions, you can do all kinds of stuff with it. But the root mean square is a statistical trick to get an average for something whose average is actually 0. We know it's inflated, but that's okay. Everybody understands what's going on and we can run with it. So why am I telling you about this? This is one of the main tricks that we can use to get past the time dependence of these alternating current circuits. So let's go back to here, okay? Let's start, when we did DC circuits, it all revolved around Ohm's law, didn't it? Like everything in DC circuit was Ohm's law. And we had series and we had parallel, we had all those rules for what capacitors do and resistors do. I want to develop that toolbox, or at least give you that toolbox, okay? In the context of wink wink, we're doing AC circuits, but what we're really trying to do is DC circuits. And so the first thing we do is we go, okay, these voltages, currents, resistances, all this kind of stuff is changing in time, but we're going to pretend like they're not. So to do that, we are going to use the root mean square value for the voltage, VRMS. Okay? And correspondingly, the current is going to be the root mean square value. And instead of resistance, we are going to use a new idea called the impedance. More on that in a second. Okay, but notice how in the AC version of Ohm's law, okay, we're still got voltage, we still got current, and we still have this new thing called impedance that plays the role of resistance. It's just we're using the root mean square value. So just a little bit more on this root mean square thing. Because the root mean square is this sort of artificial average, there's actually a different value for the maximum, like the most that the voltage could ever be in an AC circuit. And it turns out to be I'm going to get this wrong, because I never remember there it is, okay? It's going to be square root of 2 times VRMS. Your book might write it as Vmax over the square root of 2, either way, okay? And this applies for current as well. Maximum current in your circuit is going to be square root of 2 times the RMS current. So basically what this means is, what's the voltage that comes out of the wall normally? Anybody know? 120? Between 110 and 120. PG&E usually takes the average of 115, but usually it's easier if we just remember 120 volts. That 120, when you're talking about AC and they say it's 120 volts and they don't tell you anything about that voltage, you always assume that is the root mean square value. Always, okay? I'll try to be clear, right, in questions I see, but I can't promise that the homework is terribly clear. But if they say an AC generator produces 50 volts, automatically what are you going to think? It's the RMS value, okay? So if you have to find the maximum voltage, so what this means is 120 volts is this kind of average idea. The actual highest voltage that could be coming out of this outlet is the square root of 2 times 120. 1.7 times 120 is about 172 volts or something like that. Square root of 2 times 120. 170? See, I can remember some stuff, right? Okay. That means that voltage could be 170. But because it's oscillating, it could also be 0, right? So now we've got a new game of roulette, don't we? Right? If I stick it in at the right time, fast enough, I could get 0 or some other value. Don't do that. Don't do that. Okay? My wife and I invented another version of roulette last night. What was it? Amazon roulette? program a web page to randomly find an Amazon page and click buy now without even looking at it to see what shows up? Yes, she said that wasn't good either. So, right? Right? Well, she came in from the front yard carrying a stack of Amazon packages this big. And I was like, what? Did Jeff Bezos come by? Like what is going on here? I don't know. Apparently we needed stuff. I don't do the shopping, obviously. My wife says I'm not allowed to. Because I get mad when I go to the store and lettuce is more than 50 cents a head. What happened to the 1930s? Anyway, where was I? Anyway, so it could be, right, 0, it could be 170, but on average, right, it's 120. So just beware, they might say a maximum voltage from an AC generator is 80 volts. What do you have to do with that number before you start doing any of the math I'm about to show you? Convert it to RMS. You want to work all of these things in RMS. All right, so this impedance thing. I never know how to present this, so I'm just going to turn on the fire hose and it's going to be okay, right? It's going to be okay? It's going to be okay. The impedance, let me get rid of this DC stuff. There's no business being here. For a series RLC circuit, circuit. I don't think I spelled that right, but oh well. Series, so not parallel. RLC for resistor, inductor, capacitor. The symbol for inductance is L. I know really I haven't talked about inductors yet. Circuit, which basically looks like this. An AC circuit, which is a sine wave in a circle, connected to a resistor, connected to an inductor, which is a coil, and then connected to a capacitor, which is the parallel plates. Okay. The impedance for this circuit, the equivalent resistance, you remember the equivalent resistance for like series and parallel? And we had all those 1/overs and stuff like that? Well, the impedance for this circuit is the square root of the resistance squared plus the quantity x sub L minus x sub C squared. In long version, it's the resistance squared plus the difference between the inductive reactance and the capacitive reactance squared. It's all clear as mud, isn't it? What the heck just happened to my life, Mr. Balogh, and can I change my major now? Okay, this is what's happening. Is a capacitor a resistor? No, right? What do resistors do? They resist the flow, right? They just like friction in a circuit, right? Okay, what do capacitors do in a circuit? They hold things, they store charge, right? The whole capacity, the ability for it to store charge, right? All that kind of stuff. So a capacitor is not a resistor. And an inductor is a solenoid. And what solenoids do in AC circuits is store magnetic field. They store magnetic flux. And because they're storing magnetic flux, it's Faraday's law, Lenz's law thing. A solenoid will always fight the change in current through a circuit. So if the current's increasing, the solenoid will push back. But if the current's trying to decrease, it'll try to help that current stay. If you've got like a laptop charging brick or a phone charging brick or something like that, it's got a little LED green light on it. If you've ever unplugged it and like the green light stays on for a while, there's an inductor inside that brick. And it's trying to keep the current flowing. It's stored energy in magnetic field, and when you unplug it and cut the current, it'll try to keep that going. And some of those LEDs like stay on for like 30 seconds, don't they? Right? So an inductor, so where capacitors store electric field to push charges around, inductors store magnetic field to push charges around. So, is an inductor a resistor? No. Right? So what are we going to do? We're going to treat everything like a resistor. We're going to turn the capacitor into a resistor. Makes sense, right? Okay. We're going to turn the inductor into a resistor. It's just like, just go with it. Really, live the lie. It's so much better. Okay. It gets worse before it gets better. This is the capacitive reactance, according to your book, is 2 pi f, where f is the frequency, times the capacitance. And then this isn't right. My notes are wrong. That was not right. That is not right. Sorry. This is capacitance over 2 pi f. No, it's not. 1 over 2 pi. And there we go. Now we got it. And then the capacitive inductance is 2 pi f times L. There we go. Those are correct. All right. What has just happened? Oh, by the way, you will see this written as 1 over omega c and 1 omega times L. So here's reaching way back into physics 2a, unit 4. Waves, sine, cosines, omegas. Remember how I admitted to you that omega isn't really angular velocity, it's angular frequency, right? Because omega is equal to 2 pi f, you can write them either way. Your book chooses to do the 2 pi f's in there. So frequency in hertz. Anybody remember what the units for omega were? It's radians per second. Okay. Anyway, everywhere except your book usually uses omega. Now, again, we're hiding a lot of these wiggles, aren't we? But the wiggles are sort of lurking in the background, ready to bite us. Okay. So, which is why omegas and frequencies are like showing up here, right? To be able to describe a wave, to be able to describe an alternating thing, we have to be able to think about its frequency and angular frequencies and all that kind of stuff. So what the heck is going on here? The capacitive both of these x's right here are called reactances, okay? And you can say capacitive reactance, so we're talking about the capacitor, or you can say the inductive reactance, talk about the inductor. These are, again, lies where the units of these reactances are ohms. Don't try to figure that out. Okay? Just go, okay, Mr. Balogh, I'm willing to believe anything you say. Okay? It's important that you understand that we can theoretically turn a capacitor into a resistor in an AC circuit. Can't do this in DC. But in an AC circuit, we can turn it into a resistor, or something that acts like a resistor. Same thing happens with the inductive reactance. We can turn the inductor into a resistor in quotes. XML and XMC have units of ohms. Resistance has units of ohms, right? And so that's why we can subtract and add them and square them and do all kinds of stuff up there. That impedance that I've given you up here only works for that circuit right there. As soon as we try to do a parallel branch, we actually have to rederive the impedance for that parallel circuit. And then if you mix series and parallel, you got to go back and you got to rederive the impedance for that. So AC circuits gets really bad really fast once you start doing other circuits, which is why at this level we only stick with this one. So the good news is, because of this big lie, we don't want to teach you how to derive impedances, we are only going to stick with a series RLC circuit. You will never encounter a circuit that's an AC circuit that has parallel combinations. Okay? We reserve the right to maybe just have an RL circuit where we drop out the capacitor. And I'll show you how to deal with that. Okay? Or we might have an LC circuit where there's no resistor, right? We can plug in variations on a theme of things being in series, but we're never going to give you a parallel combination. Okay? All right, so we've got our impedance. We've got a way to turn inductors and capacitors into resistors, effective resistors, and we know Ohm's law for our circuit. What's left? A couple things, unfortunately. Okay. The average power consumed in an AC circuit. Do we remember? Do you remember what average power was in a DC circuit? Last unit. That was so long ago, Mr. Bailey. That was before I knew about 3 different right-hand rules. Wasn't it current times voltage? Power was current times voltage, and then we could swap in I squared R or V squared over R or something like that. Well, in AC circuits, the average power is IRMS, VRMS, just again being very careful that we're remembering these are RMS, times the cosine of phi. What's phi, you ask? You don't want to know, but it is. The cosine of phi is equal to the true resistance divided by the impedance of the circuit. Phi is often called the power factor. Again, the power varies depending on what the circuit is doing. Okay, again, because it's oscillating. But this average here is a way for us to kind of capture, this is about the power that we're doing. It's not instantaneous, it's just happening most of the time. All right. You know, I'm just going to complete the toolbox. We're going to talk about this at the end of class. The resonance frequency for a series RLC circuit is this. And I'll talk about what resonance frequency is later. Okay. So at least you have all of the toolbox in one spot in the PDF for what we're about to do. I know that you're sitting there going, okay, great, we're lying, Mr. Balogh. What does this have to do with me? Just show me how to use it. So I wanted to show you how to do it. We'll get past that. And then I want to show you why it matters to you. Because something that you count on every day is directly influenced by everything that you see on the screen right here. And I'll get there. But let's do examples of how we use this toolbox, okay? So I got like 3 different examples here. Again, this is just templates for you, methodology for working through any AC circuit problem that we may throw at you or the MCAT may throw at you, okay? All right, so you want to identify what your voltage source is doing, right? So it's AC, alternating current, and they gave us a frequency of 100 hertz, right? That hertz right there is the frequency F. So if you see examples where they're giving you a frequency in radians per second, what is that? That's omega, isn't it? Right? So just remember 2 pi f equals omega, and you can go back and forth between them. So we know our frequency is 100 hertz, and we know our RMS voltage, okay, because they tell us it's RMS, because apparently I wrote this problem. Not all homework problems do that, it's kind of annoying. Okay, so this generator is connected in series. So we have our AC source connected in series with a resistor and a capacitor. So no inductor is in this circuit. I usually draw just a really simple picture. Again, visually for me, being able to anchor my brain to something really, really helps. Just refer back to, okay? And they want to know what the current is in this circuit. So if they're asking you for current in the circuit, back when we did DC circuits, we had to take that circuit and remember series and parallel and mush it all down to a single circuit that was just a battery connected to some equivalent resistance. And then once we knew what the battery voltage was and the total equivalent resistance of the circuit, we could find the current in the circuit and then work our way back out again. We're doing that, with AC circuits. But the good news is that there's no parallel connections. Okay, so how do we do that? What we have is VRMS, come on, VRMS, and we know that Ohm's law tells us that if we know the voltage, current, and resistance, in this case the impedance, we should be able to solve for this. In other words, my RMS current in the circuit is going to be my voltage divided by my impedance. So the goal here is to find the impedance of the circuit. Impedance in this kind of circuit is the square root R squared plus, and again, it's a difference between the inductor and the capacitor. It's inductor first, capacitor second, last subtracted, okay? And one of those is an L, one of them is a C. There's a C. Okay, so to be able to find the impedance, what do we need to calculate? We know the resistance. But what are the other two things we need? XL and XC, right? You can call them that. You don't have to call them the inductive reactance and the capacitive reactance. This is just big words to make, give physicists job security or something. I don't know. So, what is XL in this problem? It's 0. There's no inductor here, right? Okay, so we just put 0. Yeah, nice. Okay. X sub C. Do I have notes for this one? Yeah, I do. Look at that. I amaze myself sometimes. Okay. X sub C, that is 1 over 2 pi F times the capacitance. So that's 1 over 2 pi. What's my frequency? 100 hertz. And what's my capacitance? 0.25 microfarads. 0.25, what's micro? 10 to the minus 6. And so I throw that into my calculator and I get 6,369. 6,369 watts. What are the units? Ohms. And why is it ohms? Because I said so. About the only time in this class I say things like that, right? But AC circuits, you just go with it. You say, okay, fine, right? I'm giving up as long as you put that capacitance in its standard unit, right? You can't put in just 0.25 and just go with it, right? You got to make sure that microfarads gets converted to farads. Okay, so there's the effective resistance of my capacitor, which means I can come up here and I can calculate my impedance. That's going to be the square root of 10,000 squared plus 0 minus 6,369 squared. What happens to the minus sign? When you square something that's negative? Positive. So I don't have to worry about imaginary. I mean, I am doing imaginary physics. I've always thought of AC circuits as imaginary. Because it's like, well, this isn't real. The annoying part is that it works. 11,856. What are the units? Ohms. Okay. And now that I know the effective resistance of my circuit, I can come up here and say, okay, well, IRMS is equal to my voltage RMS, which was 20, divided by 11,856 ohms. And everybody knows that when you take a volt and divide by ohms, you get an amp, right? Yeah, whatever. 0.00169 amps, or 1.69 milliamps. Okay, let's take a step back here. The actual number of the answer doesn't matter. What did we do? What are our steps for working through AC circuit problem? What's a very important thing to find? What?
Saying your sanity.
Your sanity. Yeah. Don't change your majors yet. This only happens for today. So what are some key things that we had to find to be able to unlock all of this? these XCs and XLs, right? So at the very least, if you're given a capacitance, find XC, right? If you're given an inductance, by the way, the units of inductance are henries. You can have a millihenry and a picohenry, and a nanohenry. It's cute. The last name of the guy. Anyway. So you could have an inductance, right? If you're given something in millihenries or henries or whatever, change that, right? Find X sub L. Resistance is just resistance, so that doesn't change, right? Once you have X sub C and X sub L, find your impedance. You're gonna need it. So just calculate it. And then kind of figure out what the question is asking you to find. In this case, I wanted the RMS circuit and current in this circuit, so I just solved for it. Right? A lot of this is just turn the crank. The hard part is just putting the pieces together and giving up on any understanding of what's going on. Because take it from me, you do not want to understand what is going on. I thought for a little tiny bit that I wanted to be an electrical engineer when I grew up. I saw this and I ran to physics. Physics was easier. Quantum mechanics was easier than this, as far as I'm concerned. Same thing happened with organic chemistry. I think quantum mechanics is easier than organic chemistry, but a lot of chemists would disagree. Anyway, different stories for different folks, right? What the heck is going on? Okay, before I even realize what they're trying to tell me, I'm gonna find X sub L. How do I know it's X sub L? What is MH? Millihenries. Okay, so that's an inductor. Okay, it says a 255 millihenry inductor. Okay, so I better find X sub L right off the bat. That's going to be 2 pi f times the inductance. Did they give me a frequency? Oh, 60 hertz. And then what am I going to multiply by? It's going to be 255. What's milli? 10 to the minus 3. Okay. And now that I've made sure to put everything in their standard units, I should get ohms out, right? Well, I'm going to hope. This is 96.1 ohms. All right. Now that I know that, what's my X sub C in this problem?
525.
It doesn't say anything about a capacitor, does it? So that means my impedance is the square root of R squared, right? Plus X sub L minus X sub C quantity squared, which is going to be the square root of 525 squared plus 96.1 minus 0 squared on my calculator, and that gives me 533.7 ohms, because impedance is ohms and X's are ohms and everything's ohms except for currents and voltages. Okay, so now that I know that, what are they? Okay, now that I know these things, now I come to grips with what the question is trying to get me to do. What is the current in the circuit? Do I have something that relates current, voltage, and impedance? Ohm's law. VRMS equals IRMS times the impedance, so the current is going to be VRMS divided by the impedance, and my voltage is 20. My impedance is 533.7, and when I do that, I get 0.0375 amps, or 37.5 milliamps. It really is just turn the crank. I'll give you why here in just a little bit. I'm trying to show you how to survive questions that will be thrown at you, right? Find X sub Z, find X sub L, find your impedance, figure out what they're asking. Okay, and then go for it. And it feels like I'm moving fast in these examples. I am. I don't like this stuff. Oh my gosh. I have a resistance, I have a capacitance, and I have an inductance. My life is over. What are we going to do? First step. Since we have a capacitor, are we going to find X sub C? Yeah. How do we find it? 2 pi f times the capacitance, right? So it's 1 over 2 pi 60 hertz for the frequency times my capacitance. It says 0.15 funny curly UF. What does that mean?
Times 10 to the negative 6.
That's times 10 to the minus 6. That's the symbol for micro, isn't it? I have that one. Thank you, pass me. I got 17,683 ohms. All right. Is there an inductor in this problem? Yeah, look at the Henrys are right there. 2 pi f times, oops, my inductance. That's 2 pi times 60 times 25 millihenries. What's milli? 10 to the negative 3. Gonna get me 9.425 ohms. That's not 9,000, that's 9.425. So the capacitor is acting like a 17 or almost 18,000 ohm resistor. And the inductor is acting as a 9 ohm resistor. Who wins? The capacitor by a long shot, right? So the inductor is hardly doing anything in this circuit. That's kind of interesting. Don't care why that is. All right, now that I've got those two, I can find my impedance. That's going to be R squared plus X sub L minus X sub C. You got to subtract them before you do the squared. It's not X sub L squared minus X sub C squared, right? You got to subtract and then do the squaring. So this is going to be number-wise 9.9 kilo. Oh, that's 9,900 squared plus 9.425 minus 17,683 quantity squared. It's like, why bother? This gets me 20,257 ohms. So there's my total resistance of my circuit. I know my RMS voltage is 115. What do they want to know? They're not asking me for current. They're asking me for the voltage across each element in the circuit. In other words, what's the voltage across the resistor? What's the voltage across the capacitor? What's the voltage across the inductor? This is a little bit like after in DC circuits we've gotten down to that equivalent and now we're working our way back out to find out what the currents and voltages are across the individual pieces. This is similar to that. So, okay, I'm going to want a picture just to make sure that I am thinking about this right. So basically, I've got my resistor, my inductor, my capacitor, right? I need to be able, okay, so it's in series, and what can you tell me about what is same when it comes to series? Current, right? Whatever amount of charge, guess, whatever amount of charge flows through that, coming out of that generator, has to flow through the resistor, then the inductor, then the capacitor, right? You can't, there's no other pipes for it to go, no other places for the charge to go. So I know that the current has to be the same. So that means I better find out what the current is. And how do I find out the circuit current? We've done it twice already, right? Take the voltage, divide by the impedance. Again, the impedance representing that equivalent resistance for this whole circuit put together. So That's gonna be 115 volts divided by 20,257 ohms. Which when I did that, I got 0.0057 amps, 5.7 milliamps. Okay, so now that I know the current in the entire circuit, and because the circuit is a series circuit, I know the current in everything. I know the current through that resistor, I know the current through that capacitor, and I know the current through the inductor. So let's answer the question for the resistor. How do I find the voltage across the resistor? Just go back to DC. If I told you that the current was 0.0057 and the voltage was 115, how would you find? Other way around. The resistance is 9,900. How would you find the voltage? Meditate on it. Ohm's law, right? Ohm's law will give us that. So for the resistor, it's V equals IR. We just want to know the resistor, right? We don't want to know anything else. So that's going to be the current, 0.0057, times the resistance of the resistor, 9,900 ohms, which gets me 56.43 volts. So there is the voltage across the resistor. If I want to know just the voltage across the resistor, I take its current, multiply by its resistance, and I'm done. And we're going to do exactly the same thing for the other two elements. So if I want to find the voltage just for the inductor, we'll do it for the capacitor first. No, we'll do it for the inductor first. Why not? That's going to be voltage. The voltage we're trying to find is going to be the current in the circuit. And then what are we going to put in for the resistance? Just XL, right? Not the whole impedance, because that would be the whole circuit. I just want the voltage across the inductor, so I'm going to use the inductor's resistance. It's going to be 0.0057 times 9.425, which gets me 0.054 volts. And then the capacitor, it's going to be current times what? XC, just the resistance of the capacitor, 0.0057 times 17,683, which gives me 101 volts. So there we are. We found the voltage. How do we check this? Is there any possible check? Not really. Just make sure you use your calculator right. One of the things you might be tempted to do, which you are not going to do, okay, is you might be like, oh, well, I should be able to add all of those up and get to the voltage that's coming out of my generator, right? I mean, energy has to be conserved, doesn't it? And electric potential or voltage is related to electric potential energy. What happens if you add all three of those numbers up? You get a number way bigger than 115, don't you? So in this lie, have we just broken all of physics? You can't just add all of those voltages up. What are those voltages? In every AC problem, what is the voltage? If it's not specified, what do you assume? The root mean square value. Coming back to those phasors and all of those squiggly lines I was showing you in that simulation. The resistor, the inductor, and the capacitor never hit maximum voltage at the same time. In fact, they never hit their RMS voltage at the same time. They are all offset from each other with those rotating vectors. They're all offset just the right amount to make sure that the voltage in the circuit never deviates from 115 volts. At any one instant in time, we could find the voltages across all these things, and they would add up to 15. But these values are not instants in time. They're this weird average, this root mean square value that strips time out of this to ideally make it easier for us to work with AC circuits. So when an electrician has to come to your house to do repairs, they're counting on the fact that the outlets and things that you plug into them are rated for the root mean square value for that voltage. Circuit breakers, everything, all appliances are standardized on this cheat. Because it's just easier to deal with the cheat than it is to actually require everybody to know differential equations just to plug in their toaster. It just works. And it works actually really brilliantly. It's fantastic how well this cheat works. And I'm indebted to electrical engineers, very smart people that like doing a whole lot of math, who figure these things out so that I don't have to, right? I can go off and do quantum mechanics and tell them, well, why their wires work in the first place. All right, so let's start bringing this home to why this matters. Like, why don't we just skip this chapter? If we're just lying anyway, mister, we could probably say that about all of physics, right? We're just lying about friction, Mr. Balogh. Why did we do physics 2A? So, it's problem solving, it's giving you context for applying your mathematical skill, but I think this is the punchline right here, and it has something to do with resonance, which is something that we studied back in physics 2A, so I gotta review that with you a little bit, okay? Before we can jump in to why this is so powerful and how this affects your life on an everyday basis all the time. But didn't affect your parents' lives or your grandparents' lives. Resonance first. Does anybody remember what resonance was from physics 2A? No? No? It was in waves. We were talking about waves, and more specifically, springs bouncing up and down, okay? And I think I used an example of swinging on the swings. Like when you swing on the swings, when do you do the kick? At a certain place, right? You always do it as you're swinging, like you just come back and you're starting to turn around, and that's when you add energy to the system, right? If you try to swing at random times, your amplitude is just going to fall off, right? If you're pushing a kid on the swings, you always push them at that same point in the swing, right? You don't go run up and push them at a different part, unless you're cruel, okay? So, resonance is an increase in amplitude of an oscillating system when you push it at the frequency it wants to be pushed at. Everything, the desk, you, me, the air, has a resonant frequency, a vibrational frequency that when it experiences that frequency, it'll get excited. It'll start to vibrate strongly. AC circuits are no different. AC circuits are like springs in the sense that they wiggle back and forth. And so it should come as no surprise that if we push an AC circuit at a frequency that it would naturally want to vibrate at, we will get this increase in amplitude, in this case, of the current in the circuit. When an AC circuit is near its resonant frequency, the current will spike. You'll get a really big current. Okay? It's like the kid on the swings. You push them a little bit, but their amplitude keeps getting bigger and bigger and bigger. Okay, to a certain point, you can't get them to go over the top, right? Okay, same thing in a circuit. It'll get to a certain point where it gets maximized. If you're not at the resonant frequency in a circuit, then that's like trying to swing and pump at random times. The current will just kind of fall out, right? You'll get different parts of the circuit fighting against other parts of the circuit. But at resonance, the circuit is all kind of swinging together and gives rise to this big current. What the heck is this picture? Okay. what the book and what a lot of physics education at this point tries to do is they try to give you a sense that the thing that's going on in the circuit is very similar to if you had a mass on a spring. When a mass on a spring bounces back together, we get maximum potential energy when the mass is way out here, right? And maximum kinetic energy at the middle. But it's usually at this point, or probably about 5 minutes ago, when you've just stopped paying attention to me, because you're just like, I don't know what you're talking about anymore, right? Which is pretty normal for every class, right? But again, the analogy is there. A circuit is like a mass on a spring. To a physicist, I mean, you're sitting there going, no, those two things are not the same, Mr. Bailey. Right? To a physicist, they are. They're both wiggles. And to a physicist, it doesn't matter if it's a physical wiggle of a mass or the wiggle of a charge. You've got wiggles. And if you got wiggles, you've got frequency, you've got wavelength, you've got resonance. And why does resonance matter? Oh, by the way, the resonant frequency. Oh, I put it down on the cheat sheet, the toolbox already, right? In your book, it was one. Your book's using different symbols. It's 1 over LC for me. 2 pi. Because I always use omega. Anyway, all right. So notice there's no R in here, right? So we're doing resonance for LC circuits only. When you have a resistor in there, the resonance gets damped. It's like the kid on the swings, right? There's a certain amount of friction in that system so that you can't get them to spin over the top, right? That's what resistance does. But without a resistance, the equation's much simpler, and we can basically tune any circuit based on inductance and capacitance. Change the inductance, you change the resonant frequency. Change the capacitance, you change the resonant frequency. And why would you want to have control over the resonant frequency of a circuit? What's that?
Radio.
It's a radio. Nobody uses radio, Mr. Balogh. Yes, you do. You use radio all the time. Where are you using radio? This thing is garbage without its internet connection, right? Like I can play games on it, and anything I've managed to download to it, but if it doesn't have an internet connection, it's like, what is this thing for? Right? The utility of these devices depends on their ability to talk to all the servers, to steal our personal information, all that kind of stuff, right? So I looked for examples of like radios, okay? I found this picture. I want to meet that person. That is awesome, right? Okay? But cellular is a radio signal. We're going to talk about what radio waves are next. And by next, I mean after your exam. Okay? Because this is where we're going. Okay? But suffice it to say, when your parents and grandparents grabbed that knob and turned it, they were changing the value of a capacitor. Let's back up. How many radio stations are broadcasting at the same time? All of them, right? It's, you know, if you've ever tuned a car radio, right? You tune to 105.7, whatever, blah blah blah, right? Okay, and they got their call sign. But 105.7 is broadcasting at the same time as 101.3 or 96.4 or whatever, right? However discreetly your radio can tune, right? All of those frequencies are happening at the same time. In other words, the antenna on your car is picking up all of the radio stations at the same time. It can't help it. It's an antenna. And what do antennas do? Pick up radio. That's like their whole job. So why is it when you tune a radio that you don't hear all the stations at once? The specific frequency is causing what to happen? You change the circuit's resonant frequency. It's receiving all of them, but there's only one frequency that's going to cause the circuit to get happy and have a really big current. And it's the frequency of the channel you are tuning to. All other channels are received, but they don't cause any resonance to happen. And so it's that turning of the dial, changing usually a capacitor in the circuit, that will change the resonant frequency that allows you to tune you're changing the tuning, literally like stretching a string on a guitar. You're changing the frequency that the system wants to vibrate at, and that's the channel you are going to hear. Because the radio circuitry says, that's the big current, make that one come out of the speakers. If you've ever listened to radio out in the middle of nowhere, I'm not talking like Pixley and Dinuba, right? You might get, have you ever heard two stations going on at the same time? Okay, right? There, you got two stations that are equally far apart, they're on the same frequency, okay? And so now the radio doesn't know which one's supposed to be the maximum, they're both the same about level, so it goes, okay, well I'm just gonna give you both. So you get the Christian station and the country rock station at the same time, and it's an exciting thing, right? So what does this have to do with like modern stuff? Your phone receives maybe 5G, definitely LTE. It also receives Bluetooth and cellular voice and cellular data and cellular message. There's a lot going on. There's like 5 or 6 antennas in your phone, in your watch, and anything else that's connected to the Wi-Fi. If it does Bluetooth and Wi-Fi, that's at least 2 different antennas, okay? And then if it does anything else, you just add on a whole bunch of antennas after that, okay? All of those antennas are picking up different, they're designed to pick up different frequencies, okay? But within each of those systems, when you're tuning to Bluetooth, that's a different frequency. And so the Bluetooth antenna and all the circuitry that's attached to it resonates with that Bluetooth frequency. Same thing for the Wi-Fi, right? Its antenna and the circuitry attached to it only resonates to the frequencies that are being given off by the Wi-Fi antennas, right? And then the same thing happens for the 5G and LTE. And so when your phone tells you that you've attached to the Wi-Fi, that's true, you've attached to the Wi-Fi. But has it shut off its 5G? No. It's just preferring, the operating system says, oh, okay, I'll get the data from Wi-Fi because that doesn't cost money. Right? Okay? But your phone does receive all of the radio frequencies that are being given off all the time, everywhere around us. How does the phone or the radio know which channel or station you want? Set the resonant frequency. Luckily, we don't have to manually go in and set resonant frequencies for Wi-Fi. Old Wi-Fi had 12 different channels. New Wi-Fi has 160 channels, right? Okay. And the sophisticated software on our phones and in these antennas and stuff, they'll do channel hopping so that if everybody's trying to do channel 142, it might bump you onto channel 10, right? One channel isn't any better or worse than another. It's just a different channel so we don't get all kinds of disruptions. The other thing that these things do is we don't all talk to it at once. There's actually sharing of information, and it just happens fast enough that we think it all happens at once. Except for that one class where everybody did hit it at exactly the same time when you're trying to do the Moodle quiz or whatever, right? Okay? And then what happened to the Wi-Fi in that ring? Died, right? And why did it die? The software got overloaded. And it just says, I'm done. Without AC circuits, we couldn't have wireless transmission of information. Without AC circuits, we could not have electricity wired into our homes. And both of those things are brought to you by Faraday's law of electromagnetic induction and our understanding of Lenz's law. Both of which are brought to you by our understanding of how magnets work. All of this is leading to the modern world that we know and love. And what we are about to do is take a step towards figuring out how that modern world works. After your exam on magnetism, Faraday's law, and AC circuits, all this kind of stuff, what we're going to do is we're going to transition into optics. And I know that sounds like it's not related, but it is very much related to everything that we're talking about. So the good news is that it gets easier. Optics is just easier, right, than what we've been doing so far. And in a lot of ways, for me, it gets a whole lot more exciting. Spoiler alert, or maybe just full disclosure, I'm an optical physicist. My specialty is optics. We're gonna have fun. Because there won't be AC circuits anymore. I'm done. That was that chapter in one day, right? How many homework problems did I get for this chapter? Yeah, it's like small, isn't it? Yeah, okay. So what does that mean you get to spend time reviewing? Right hand rules, right? You know, I get that. What's happening for grass tomorrow? Nothing, right? I will be here at my normal time, like at 7. It's just I'll be in my office, so if you're here around 7, you can stop by if you want. But starting at 8:30, I gotta focus on limited engineering stuff. So I'll be around. If you're around and you need help with something, just come in real quick. But otherwise, go to the tutorial center. Have a great weekend. I will see you on Monday. We'll actually do a lab on Monday. No, shocking. Well, hopefully not shocking.